Hello, this is going to be your 4.8 lecture. You didn't miss anything. 4.7 is not a section we are covering this semester. So the title of this is Antiderivatives, so it shouldn't be a surprise that this is going to have something to do with the derivative. Let's start with the definition. So a function cap f is an antiderivative of little f on an interval I if cap f prime of x is equal to little f of x for all x on that interval I. Generally, these intervals are going to be all real numbers for us, or at least the domain of the function, so don't worry too much about the interval part. So this is pretty straightforward. If you are looking for an antiderivative, you're looking for the function that you would need to take the derivative of to get back to the function you have. So for instance, if f of x equals 2x, then an antiderivative of this is equal to x squared, because the derivative with respect to x of x squared equals 2x. So this is kind of old school. Like if you think back to, I don't know, second or third grade when you were first learning about division, we would tell you that 8 divided by 4 equals 2 because 2 times 4 equals 8. So this is an inverse process of taking a derivative, and it's a pretty straightforward one as it goes. If you've got a pretty good grasp on your derivative rules, you won't have any trouble coming up with your antiderivatives. So for example, the function g of x equals cosine x. An antiderivative of this is g of x equals sine x, cap g of x equals sine x. The derivative of sine is cosine. Another derivative of this would be sine of x plus 2, though, because the derivative of sine of x plus 2 is still just cosine x. And in general, these constants are going to be kind of, what's the word? We're going to be able to use them, change them. They're just going to be a fact of life for antiderivatives. So instead of getting a single antiderivative, you're going to get a family of antiderivatives. So all antiderivatives of g of x equals cosine x have the form cap g of x equals sine x plus c, where c is an arbitrary constant. So any constant added to sine is not going to change the derivative of this function. As a matter of fact, this is called the most general antiderivative for cosine x. Having trouble getting this camera to stay in focus just like on the last one, so I'm going to leave that there as I start to write the next page, but I'll get rid of it in a minute. So if we have h of x equals 1 over x plus 2e to the 2x, and I want to find an antiderivative of this, I can find an antiderivative of this guy separate than an antiderivative of that guy. So an antiderivative of 1 over x, what do we take the derivative of to get 1 over x? That's going to be the natural log of x. Except we don't know that x is positive, and natural log will only accept positive, so we're going to use an absolute value there. Plus, you see I've got that 2 out front there. Normally that's going to pass right through, but if I think about this, the derivative with respect to x of e to the 2x would have been 2e to the 2x. So this will be my antiderivative, e to the 2x. You just got to think about, well, what would I have had to take the derivative of to get this? Now we have a bunch of formulas for this. Oh, sorry. And if I want it to be the most general antiderivative, then I just add a c at the end. So we've got a bunch of formulas because we have a bunch of derivative formulas. So if I want to find the antiderivative of x to the n, f of x equals, I need to think about what I would do, what I would take the derivative of to get this. It'd need to be an x to the n plus 1, but if I take the derivative of that, I get an n plus 1. So I'll divide by it there. And so now take the derivative of this, the n plus 1s would cancel, and I'd have just x to the n plus c. This is for n not equal to -1, because that doesn't exactly work here when we can't divide by 0. Let's see. You know what, I'm going to introduce some notation here. So instead of just using lowercase letters and capital letters to refer to our functions and their antiderivatives, I can say that f of x, the antiderivative of x, is this symbol here, is a big swoopy S, and it stands for, it's an integral symbol. So this will say the antiderivative of f of x with respect to x, because keeping in mind, we're talking about taking the derivative with respect to x, we're talking about taking the antiderivative with respect to x. So I'm going to use this notation to make our table. So the antiderivative of x to the n with respect to x is 1 over n plus 1, x to the n plus 1 plus c. What else do we have? We got a bunch of trig formulas. So the antiderivative of sine x is equal to negative cosine x plus c. There's another thing going on here. If I had a constant in there, the antiderivative of sine of kx with respect to x, would be equal to, so if I just took cosine kx plus c, and I took the derivative of this, I'd get a k out from my chain rule. So if I just divide by that k, this is an antiderivative of sine, and the most general antiderivative has the plus c. Except I forgot my negative sign. Negative 1 over k cosine kx. Similarly, antiderivative of cosine kx. So the thing I take the derivative of to get cosine is sine. So that'd be sine kx over k plus c. And I need my dx. Those are important. I know I'm not making it look like they're important, but they are important. And so for each of our trig formulas, antiderivative of secant squared x with respect to x is just going to be tangent x plus c. Antiderivative of secant x tangent x with respect to x is just going to be secant x plus c. And so we've got a bunch of these. I'm not going to go through them all, but let me see. Here we couldn't let n be -1 before, so antiderivative of 1 over x dx is equal to the natural log of the absolute value of x plus c, so long as x isn't 0. We had e to the kx already, so the antiderivative of e to the kx dx is 1 over k e to the kx plus c. We have some inverse trig formulas. So for instance, antiderivative of, I'm just going to do these without the k here, so 1 over root 1 minus x squared dx is equal to sine inverse of x plus c. And Another common one that comes up is 1 over 1 plus x squared. The antiderivative of that is going to be tan inverse x plus c. So let's do a couple quick examples here. So let's find the antiderivative of x to the 5th dx. So we're going to need to count our exponent up instead of down, and we're going to need to divide by the new exponent. So this will be 1/6 x to the 6th plus c. But the antiderivative of 1 over root x dx. Here it'll be easier for us if we write this in exponential form, so that's x to the minus 1/2, the antiderivative of that. And so I need to increase my exponent by 1, so that'll be x to the 1/2, and then divide by the new exponent, so that's actually 2 times x to the 1/2 plus c, and if you'd like, you can write that as 2 root x plus c. About the antiderivative of sine 2x dx. So that's going to be, so to get sine, I need to take the derivative of minus cosine, but let me put that further out there, and I need to divide by that 2 as well. So minus 1/2 cosine 2x, sorry, plus c. What about antiderivative of e to the minus 3x dx? Well, e to the x is really nice, right? So that's just got to be e to the minus 3x, except I need to have negative 1/3 that plus c. I am going to do some sort of a skills test for integration, and you'll just have to be able to crunch out a bunch of these and a few others. We've got a couple other things before we get to the skills test. Don't worry too much about that. Like, we have exam 3 before our skills test. We got a few weeks actually before that skills test. Don't even worry about that at all right now. Some properties of the antiderivative. So the antiderivative of c times f of x is equal to c times the antiderivative of f of x. There I go, not writing my dx again. The antiderivative of f of x plus g of x, or minus for that matter, is equal to the antiderivative of f of x dx plus or minus the antiderivative of g of x dx. So I can take it term by term. I can take the antiderivative term by term. And I already did that in like one of the first examples. So that's really not that big a deal. Your book makes a big deal about something called initial value problems, and you're going to see a lot of them. Essentially, oh, don't do that. Hang on, I've got to get it to focus again. Almost. There we go. Essentially, if I take an antiderivative, let's suppose I have that the derivative of y with respect to x was equal to some function of x. Then y is some particular antiderivative of x, right? It is some antiderivative of f of x with respect to x. But we don't know which one, and we get a whole infinite family with various constants. But if I put with this that I know that, say, y of 0 equals 1 or something like that, then when I put this in, it'll pick the constant that it is. So for example, the derivative of velocity, this is your acceleration, right? With respect to t, you might get negative 32 feet per second squared. So if I told you that I dropped something off of a building, then that would tell you that the initial velocity was 0 because when I dropped it, it had no velocity. And so if I told you, if I wanted to know the velocity after 3 seconds, I could say v of t equals antiderivative of negative 32 dt, which is equal to negative 32t plus c. Then when I take a look at this, I now have enough information to see that v of 0 is on the one hand 0, and on the other hand, it's equal to negative 32 times 0 plus c. So my c in this case is 0. So it pins it down to a unique solution. There's only one velocity function that has this acceleration and an initial velocity of 0. There's a different one if I had thrown the ball downward, or if I'd thrown the ball upward with a specific velocity, I'd get a different solution. And so you just plug in and algebraically solve to get that your particular velocity has the function negative 32t. I told you I dropped it off of a building. I can actually go further than this. I can tell you that the height of that building was 100 feet, which means that s of 0 equals 100. And we can figure out the height of the object, or the distance that the object is traveling, the position, I should say, of that s of t equals, or I should say ds dt equals v of t, which means that s of t equals an antiderivative of v of t dt. So an antiderivative of negative 32t dt gives me negative 16t squared plus c. Now I need to use this initial condition, s of 0 equals 100, and it's equal to negative 16 times 0 squared plus c. So c equals 100. So s of t equals negative 16t squared plus 100. And for all of you that remember high school physics, that is what our formulas gave us back then. But we just did it based on formulas. But all of those formulas came from integrating something like negative 32 feet per second squared, or negative 9.8 meters per second squared if we had wanted to do something in metric. So I think that's it for 4.8. Have a good one.